This video covers discourse parsing. I'll provide an overview of discourse parsing before focusing primarily on rhetorical structure parsing. I'll work through a case example showing how a shift-reduce parser could extract a rhetorical structure tree from an input block of text, and then briefly go over how Penn discourse tree bank parsing would differ from rhetorical structure parsing. We've covered a couple different discourse models, including rhetorical structure theory and the Penn discourse tree bank. However, we haven't yet explored how the discourse relations in these models might automatically be mapped to natural language sentences. The process of performing this mapping is called discourse structure parsing, and specifically, it is concerned with automatically assigning relations from a given discourse model to text spans from a given input. In this way, it's actually quite similar to what we saw earlier this semester with constituency or dependency parsing. The input text is broken into meaningful subunits, and those subunits are organized in a set of directed and possibly hierarchical relations. The first step, in which the text is broken into meaningful units, is generally referred to as EDU segmentation. The discourse parser is concerned with identifying the beginning and end of each elementary discourse unit present in the text. In the example here, there are 3 elementary discourse units. Natalie said is one unit, there were no office hours on Thursday is another unit, and because it was Thanksgiving is a third unit. Elementary discourse units are more or less equivalent to clauses, where each clause communicates some specific thought or concept. Because of this, a simple early approach to EDU segmentation was to simply run a syntactic parser and then apply some set of rules to the output to determine which constituents were and were not elementary discourse units. More sophisticated alternatives have been applied to the task recently, with modern EDU segmentation approaches usually implemented as some sort of supervised neural sequence model. So we start out with EDU segmentation, and then as mentioned, the second step in rhetorical structure parsing is to apply the parsing algorithm itself. Essentially, we want to somehow represent each of our elementary discourse units that we've discovered in the previous step, and then somehow connect those EDUs to one another using the relations from rhetorical structure theory. As mentioned, rhetorical structure parsers are usually based on syntactic parsing algorithms. The shift-reduce parser, which you may remember from our discussion of transition-based dependency parsing in a previous module, is one example of a generalizable parsing algorithm that can easily be applied to discourse parsing. As a reminder, a shift-reduce parser can perform 3 operations. It can push an element, or in this case an elementary discourse unit, from a buffer or queue onto a stack. It can reduce or merge the top 2 subtrees on the stack, assigning a discourse label and direction from satellite to nucleus, or it can pop or remove the final tree from the stack. We can walk through a case example to see how that works in more concrete terms. Let's say we have a sentence, Natalie said there were no office hours on Thursday because it was Thanksgiving. And we've already done EDU segmentation on it and found our 3 distinct elementary discourse units. We have an empty queue to start with and an empty stack. Let's go ahead and fill up our queue with our elementary discourse units. Now, there's currently nothing on the stack, so we can't perform a reduce or a pop action. So the only thing we can do right now is shift something from the queue to the stack. We'll go ahead and do that, so we'll shift the first EDU onto the stack as a single node subtree. So now we have 1 subtree in the stack, but in order to perform a reduce operation, we need 2 subtrees on the stack, and in order to perform a pop operation, we'd want to know we had our final tree. We definitely don't in this case because there are still multiple EDUs in the queue. That means once again we'll have to perform a shift operation, shifting another EDU from the queue to the stack as another single node subtree. Now we have 2 EDUs in the stack, so we're able to perform a reduce operation if we want to. We could also perform another shift operation, but we couldn't perform a pop operation because it's clear that we don't have our final tree yet. We'll select which action to perform next, and this might be done using rules or some sort of classifier. We choose to perform a reduce and specifically assign an attribution label to the relation between our two EDUs. We'll assign the EDU at the top of the stack as the nucleus and the EDU below it as the satellite. This, as you can see, reduced our two single-node subtrees into a single, more complex subtree. Now, we have one subtree on the stack and one remaining in the queue. We can't do a reduce because we'd need two subtrees in the stack, and we can't do a pop because there's still an EDU in the queue. Obviously, this isn't the final subtree. So we'll perform a shift action and shift our last EDU from the queue to the stack as a single node subtree. There are no EDUs left in the queue at this point, so we can't perform any more shift operations. We also can't perform a pop operation because we don't have a final subtree. There are still two subtrees on the stack. So we'll perform a reduce operation. Specifically, we'll assign the reason label to the relation between our attribution subtree and our new single node subtree. We'll set the subtree at the top of the stack as the satellite and the subtree below it as the nucleus. This results in the updated subtree that you see here. Now we have no EDUs left in the queue, and we have just a single subtree in the stack. This means that we've reached our final subtree. So we'll go ahead and perform a pop action, popping that subtree from the stack, and now we have our discourse tree. As I mentioned, there are a variety of different ways that the shift-reduce parser can select its next actions. For example, it can use a set of manually defined rules or a classification model. Modern rhetorical structure parsers generally select actions using neural networks that make decisions based on the subtrees currently on the stack and the current first EDU in the queue. This video is focused on rhetorical structure parsing because it is a relatively more complex task than Penn discourse treebank parsing, which only requires a shallow discourse parser. Shallow discourse parsing is the simpler task of identifying local relationships between text spans rather than producing a full hierarchical discourse tree. It is often done recently using supervised sequence labeling and text classification models.